Hey everyone, how are you doing? Today we're going to continue our video series on mathematical logical reasoning, and we'll talk about logical connectives which are not, and which is conjunction or which is disjunction, exclusive or conditional and biconditional. In today's video we're going to talk about the logical operators not and which is called conjunction. For those who don't know me, my name is João Sarubi, and I'm a PhD in computer science and discrete mathematics professor. But before talking about logical operators, I want to talk a little bit about George Boole. George Boole was the mathematician who in 1847 published the book The Mathematical Analysis of Logic. He proposed an algebraic approach to logic in which logical expressions and logical arguments can be represented and manipulated through mathematical operations. This was very important for discrete mathematics because he was the one who transformed propositional logic into mathematical arguments. Another very important character in history was Claude Shannon. He was the one who invented the concept of logic gates. While Boolean algebra provided the theoretical foundations, logic gates were a practical application of these concepts in engineering and in the construction of digital circuits and computer systems. These logic gates receive an input signal and return an output based on the received input. And there's a complete analogy with truth tables, which we've seen and will see in a moment. The first algebraic operator we're going to see is the negation operator not. It's not a connective because it doesn't connect anything, right? It's a unary operator. With just one proposition, I can negate that proposition. So I don't need two propositions. The symbols are tilde or the negation symbol. In English, I can substitute with not. It is not true that. It is false that. It is a lie that. Let me give you some examples. John does not like Mary. It is not true that 2 plus 2 equals 5. It is false that Peter plays football. It is a lie that man went to Mars. All these sentences, all these propositions, they use the not operator, the negation operator. Let me show you the truth table for negation. The truth table has two columns, P and not P. In the first row, when P is true, not P is false. In the second row, when P is false, not P is true. If the input receives false, the output will be the opposite. It will be true. And if the input receives true, the output will be false. Important property. The negation of negation is the original proposition. Example, it is not true that I don't like apples equals I like apples. Now let me show you the not logic gate. This figure you're seeing is the NOT logic gate. Observe that it receives one input, which is P, and the output is not P or P bar in Boolean algebra. Notice that little circle at the end of the gate. That circle indicates negation. So whenever you see a circle at the output of a logic gate, it means we're negating that output. If this video is being interesting to you, don't forget to subscribe to the channel, like, share, and hit the bell icon so you don't miss any videos. It's very important that you like the video because then YouTube sees that this video is relevant and recommends it to more people. The next operator is the conjunction operator, which we call the AND operator. The symbol is the caret or wedge symbol. In English, I can substitute with and, but, also, neither, both, and others. Let me give you some examples. First example, John likes bananas and apples. Second example, Mary is both nice and beautiful. Third example, Peter works but doesn't like his job. Note, the but here gives the sense of addition. It's a conjunction. I'm adding new information to the original statement. Fourth example, John likes neither onions nor tomatoes. Conjunction is a binary operator because I need at least two propositions to connect them. Now let me show you the truth table for conjunction. This table has 3 columns, P, Q, and P and Q. In the first row, when P is false and Q is false, then P and Q is false. In the second row, when P is false and Q is true, then P and Q is false. In the third row, when P is true and Q is false, then P and Q is false. In the fourth row, when P is true and Q is true, then P and Q is true. Conclusion: conjunction is only true when all simple propositions are true. If one is false, it will falsify the compound proposition. Let me give you a practical example to make this clear. Imagine your mom asks you, go to the store and buy oranges and bananas. Let's analyze each case from our truth table. First case, you don't buy oranges and you don't buy bananas. Did you do what mom asked? False. You didn't buy anything. Second case, you don't buy oranges but you buy bananas. Did you do what mom asked? False. She asked for both but you only bought bananas. Third case, you buy oranges but don't buy bananas. Did you do what mom asked? False. Again, she asked for both but you only bought oranges. Fourth case, you buy oranges and you buy bananas. Did you do what mom asked? True. You bought both items, so you completely fulfilled her request. This is exactly how conjunction works. It's only true when both conditions are met. In Boolean algebra, we substitute false with 0 and true with 1. The conjunction symbol is substituted with the multiplication dot. Let me show you the Boolean algebra truth table. In the first row, 0 and 0 equals 0. In the second row, 0 and 1 equals 0. In the third row, 1 and 0 equals 0. In the fourth row, 1 and 1 equals 1. Notice the analogy. 0 times 0 equals 0. 0 times 1 equals 0. 1 times 0 equals 0. 1 times 1 equals 1. Now let me show you the AND logic gate. This is the AND logic gate. It receives 2 inputs, P and Q, and the output is P.Q, which represents P and Q. This dot in Boolean algebra is equivalent to the wedge symbol we use in propositional logic. Now let's understand the relationship between conjunction and set intersection. Conjunction is directly associated with the intersection of sets. Let me show you a Venn diagram to make this clear. Imagine we have 2 sets. The first set P represents going to the movies. The second set Q represents going to the theater. Now let's say Mary went to the movies and to the theater. This proposition is only true when Mary went to both places. And where is this both in our Venn diagram? It's exactly in the intersection of the 2 sets. The intersection is that region where the 2 circles overlap. It represents all the elements that belong to both set P and set Q at the same time. So when we say P and Q, we're talking about the intersection. Mary must be in both sets simultaneously for the proposition to be true. Commutative property. Conjunction has the commutative property, meaning the order doesn't change the result. P and Q is equivalent to Q and P. Example: Mary is smart and beautiful equals Mary is beautiful and smart. In the next video, we'll talk about the OR operator and the exclusive OR operator. See you in the next video.